So, in order to find probabilities for this, they're going to act very similar to probabilities for the previous case, for the z. But we have to use a different table. We'll have right tails, left tails, both tails, all that stuff we talked about for z distributions. That's all equally applicable here. But instead of using table 8.1, we have to use table 8.3. And don't ask me why this is the way they did it, but personally, if I'd have written this textbook, I would have probably done this a little bit differently. But table 8.3 doesn't give you the left tail that table 8.1 does. In table 8.1, they give you the area to the left of z. Table 8.3, first of all, is only positive values, and it gives you the area in the right tail for a particular value of t. Okay. The way it looks, is this first column is called degrees of freedom. This degrees of freedom is the sample size minus 1. All the degrees of freedom is doing is telling you what row of the t-table to look up, what row of 8.3. It starts at 1, 2, 3, 4, and it goes down to infinity. Now, it doesn't have an infinite number of lines, obviously. Somewhere down here, it'll start jumping the number of degrees of freedom it goes. And it's on page 729. So you look at page 729. Degrees of freedom is down the left side. Across the top up here is 1.28, 1.5, out to 3.4. So these are values of t. These are degrees of freedom. The way we use this table is we find out the number of degrees of freedom for your particular problem. If I have a sample size of 5, that means my degrees of freedom is 5 minus 1, or 4. That means I'm looking at row 4 in my table. I calculate my t just like I did for the z. When you calculate t, I'll find an entry in the table. That entry is the area to the right. And then depending on whether I want left, right, or both tails, I'll either subtract that from 1 or multiply it by 2 or whatever the case might be. Okay? And we'll get into the rules. I have a set of rules just like we did for the z's, where we'll look at the form of the alternative. Based on the form of the alternative, it'll tell you which tail. It'll also tell you how to use table 8.3 to come up with a p-value. But for right now, we can simply look at this and figure it out from the fact that this is a right tail table. But remember that this table is right tails only, not left as in the 8.1 ones. Okay? It also only gives us positive values, and you'll notice it starts at 1.28. It's partially because it takes a t-value of 1.28 or more to get something that's actually interesting in terms of a hypothesis test. We have a table that I put out on Blackboard. It's a more detailed one. It actually goes all the way down to 0. So it gives you more detail so we can look at situations that are closer to the null hypothesis. Okay. So there's a lot similar. We have a little wrinkle in that we have to worry about this sigma hanging around, which means we have to estimate something else from our sample. That means that we have to get out here into something that's not quite the same distribution, but it's going to act very similar. And that new table has a little wrinkle in it in that we have to have a degrees of freedom, where we have to depend on the sample size in order to figure out the p-values. Okay? But all in all, not too bad. Questions? Are we following mostly? Let's take now and we've got plenty of time. And what we'll probably do is probably spend about 10 minutes or so, let you dig into a couple of problems, take a look at them, and then we'll come back and start working through those problems together. Okay? So take a look at 9.61 and 9.95. So 9.61 is from section 9.6. It's going to be looking at this case right here, doing some work with that case. 9.95 is going to be transitioning into working with this case here. Okay, let's walk through these. I will put these solutions up on Blackboard so you can see them later. I'll probably attach them to this same homework, so you'll see the solutions on that homework as well. 961. In 961, this is the first case that we talked about, so known sigma. What they tell us is that, I need to find 961 first. We're talking about small planes, cannot fly well with a payload, people and luggage and fuel weighs too much. Suppose an airline runs a commuter flight that holds 40 people. The airline knows that the weights of passengers plus luggage are typically customers on this flight is approximately normal with a mean of 210 pounds and a standard deviation of 25 pounds. So what they just did is they gave us the values of mu, 210, and sigma, 25. So they gave us these two values. That means I know my sigma. So I can use my z values. The first thing it asks for is draw a picture of the distribution. That I think everybody got pretty quickly, and that's nothing more than a bell curve centered at 210, plus or minus steps of 25, 3 of them in each direction. So it's around 135 to 285 that it's going to be spread out to. Okay? So you should have that down pretty well. Second step, they wanted you to describe the sampling distribution of x bar. So that was that x bar is distributed as a normal with mean mu, standard deviation of sigma over the square root of n. So that means the mean is 210, same as the individuals are. The standard deviation this time, instead of being 25, it's sigma over square root of n, or 25 over root 40, or 3.95 pounds. So that says that it's a bell curve centered at 210, plus or minus approximately 12. Okay, or 3 times 3.95. Okay? Part C says, we're pointing out that the sampling distribution has a mean much smaller than the standard deviation, and they want us to draw those superimposed on each other. And they have a bunch of stuff here about how they word this. This is rather amusing. It says, draw a picture superimposing the distribution for parts A and B. It says to label it clearly and remember that the total area under each curve must equal 1. Don't worry too much about that. All we need to remember is that there's 2 bell curves. The bell curves will have tails that touch at a certain point. Saying that the area must be equal to 1 means that when I narrow the second bell curve, when it gets narrower, it has to get taller, right? So what you're going to get is something that looks like this. The original curve is this flat thing out here that extends from 135 out to 285. And then the center bell curve is going to be much taller and extends only to 210 minus 12 up to 210 plus 12. Okay? Does that make sense? So what this is telling us is that when we take a sample and we're looking at the distribution of the averages from that sample, the distribution of the averages is going to be much narrower than the distribution of the original data. So originally this data was spread with a sigma of plus or minus, or a sigma of 25. Here the sigma is only about 4, actually a little less than 4. Okay. Anybody get part D? Even with a hint, a lot of times it's a little bit hard to get your head wrapped around what they're doing here.